The universe is expanding, and our ignorance right along with it. We live in a cosmos of breathtaking scale, yet the deeper we look, the more we realize how little we truly understand. Beyond the familiar planets and stars lies a frontier not of space, but of knowledge, filled with puzzles that defy our current physics. This is a journey through 25 of the most profound mysteries of the expanding universe, each one a crack in the foundation of what we think we know. By the end, you will have a front row seat to the greatest unsolved questions in modern cosmology. We will confront an invisible force tearing reality apart and grapple with signals from the void that hint at something we cannot explain. What single cosmic mystery keeps you awake at night, staring at the stars? The first and perhaps greatest of these cosmic puzzles is the nature of dark energy. It is the name we give to whatever is causing the expansion of the universe, not just to continue, but to accelerate. This discovery, made in the late 1990s by observing distant supernova, was a shock that overturned our most basic assumptions. We expected the collective gravity of all matter in the cosmos to be pulling things back together, slowing the expansion down over time. Instead, we found the opposite. Galaxies are fleeing from each other faster and faster, as if some invisible, repulsive force is woven into the fabric of space itself. So what could it be? One leading idea is Albert Einstein's cosmological constant, a kind of fixed energy inherent to empty space. Think of it as a property of the vacuum, a gentle pressure that pushes outward on the cosmos. The other major candidate is called quintessence, a dynamic field that could change in strength over time, more like a cosmic wind that might one day fade or intensify. The distinction is not just academic, it is a matter of cosmic life and death. If dark energy is a constant, the universe will expand forever, growing colder and more isolated in a fate called the Big Freeze, where galaxies vanish over the horizon of observation. But if it is something like quintessence that grows stronger, the acceleration could become uncontrollable, eventually ripping apart galaxies, stars, planets, and even atoms themselves in a catastrophic Big Rip. We are left watching the universe run away from us, driven by a force we cannot see, touch, or yet understand. But if dark energy is the strange force pushing the cosmos apart, there is another, even more abundant ghost holding it together. This is the mystery of dark matter. We are surrounded by it, even passing right through us, yet we have no idea what it is. All the stars, planets, and galaxies we see with every telescope we have ever built account for less than 5% of the universe's total mass and energy. Dark matter makes up about 27%. We know it exists because we can see what it does. In the 1930s, astronomer Fritz Zwicky noticed that galaxies within clusters were moving far too quickly to be held together by the gravity of their visible stars alone. It was as if the cluster was filled with some unseen, heavy substance providing the extra gravitational glue. Decades later, Vera Rubin provided even more compelling proof by studying the rotation of individual spiral galaxies. She found that stars at the outer edges of these galaxies orbit just as fast as those near the center, which defies the laws of gravity as we know them. If a galaxy were only made of the stars and gas we see, those outer stars should be drifting away slowly, like planets in our own solar system where Pluto moves much slower than Mercury. The fact that they do not tells us that each galaxy is embedded in a vast, invisible halo of something heavy, a halo that extends far beyond the visible edge of starlight. We see this ghostly influence elsewhere too. When we look at massive galaxy clusters, their immense gravity acts like a cosmic lens, bending and distorting the light from even more distant galaxies behind them. This effect, called gravitational lensing, creates beautiful, stretched arcs and rings of light in deep space images. The amount of bending we see requires far more mass than the visible galaxies in the cluster can provide. The only explanation is a huge amount of dark matter warping the fabric of space-time itself. So what is this invisible stuff? The leading candidate for decades has been a hypothetical particle called a WIMP, which stands for Weakly Interacting Massive Particle. As the name suggests, these particles would have mass and interact through gravity and perhaps the weak nuclear force, but not the electromagnetic force. This means they would not absorb, reflect, or emit light, making them perfectly dark and able to pass through ordinary matter almost untouched. Scientists have built incredibly sensitive detectors deep underground, in old mines and beneath mountains, to shield them from cosmic rays, hoping to catch the rare, faint bump of a WIMP colliding with an atomic nucleus. So far, the detectors have remained silent. Another intriguing possibility is the action, a particle originally proposed to solve a different puzzle in particle physics. Actions would be incredibly light, potentially trillions of times lighter than an electron, and could flow through the universe in vast wave-like streams. While they would be even harder to detect than WIMP, new experiments are searching for the subtle way actions might convert into photons in the presence of strong magnetic fields. The silence from our detectors is itself a profound clue. It tells us that dark matter, whatever it is, interacts with the ordinary matter of our world even more weakly than we anticipated. We are left in a strange position, mapping the contours of a shadow universe by the gravitational footprints it leaves behind, building traps for ghosts we cannot see, in a cosmos where the dominant form of matter remains a complete and utter mystery. But the dominance of matter over its ghostly twin is not the only strange imbalance in our cosmic ledger. The very existence of everything we see, from the stars to our own bodies, hinges on a profound and unanswered question. In the first moments after the Big Bang, energy should have condensed into perfectly equal amounts of matter and antimatter. For every proton born, an antiproton should have been created. For every electron, a positron, and when a particle meets its antimatter counterpart, they annihilate in a flash of pure energy, leaving nothing behind. If the universe had played by these perfectly symmetrical rules, all the matter and antimatter created at the beginning should have completely destroyed each other, leaving a cosmos filled with nothing but fading light. There would be no galaxies, no planets, no us. The fact that we are here, made of stable matter, is direct proof that the early universe cheated somehow. A tiny 1 in a billion imbalance must have tipped the scales, allowing a slight excess of matter to survive the great annihilation. This leftover scrap is what built our entire reality. So what caused the skew? Physicists call the solution baryogenesis, the process that generated more baryons, which are particles like protons and neutrons, than antibaryons. The leading clue for how this happened is a subtle breakdown in symmetry known as CP violation. C stands for charge conjugation, which means swapping a particle for its antiparticle. P stands for parity, which is like looking at a system in a mirror. For a long time, physicists believed the laws of physics were perfectly symmetric under both these operations. A reaction involving matter should look exactly the same as its mirror image reaction involving antimatter. But in the 1960s, experiments with particles called kaons showed this was not always true. There was a slight but definite preference for matter over antimatter in certain decays. It was as if the universe had a tiny, built-in left-handedness. This CP violation is a required ingredient for baryogenesis, but the amount we have observed so far in particle physics is far too small to account for the vast amount of matter we see today. It is like finding a single drop of water when we need to fill an ocean. The search is on for new, stronger sources of this symmetry breaking. This is where massive experiments like those at CERN Large Hadron Collider come in. By smashing protons together at nearly the speed of light, scientists recreate the conditions of the early universe, watching for exotic particles that decay in a lopsided way, favoring matter. They are hunting for any sign of physics beyond our current standard model, a new particle or interaction that could have tipped the primordial scales decisively in our favor. Every violent collision in those detectors is a question thrown back in time, asking the universe to reveal the secret of its own existence. Without that ancient, unexplained asymmetry, the cosmos would be a silent, empty void. We are literally made of a cosmic accounting error, the fortunate survivors of a war we never knew was fought. The cosmic accounting error that gave us existence is mirrored by smaller, more intimate puzzles closer to home. In the vast silence between the planets, two robotic messengers began to whisper a secret that would confound scientists for decades. The Pioneer 10 and Pioneer 11 spacecraft, launched in the early 1970s, were humanity's first emissaries to the outer solar system and beyond. After their triumphant flybys of Jupiter and Saturn, they coasted into the dark, their missions complete, becoming silent, drifting artifacts on an endless journey into interstellar space. Yet as they traveled, scientists tracking their precise radio signals noticed something deeply strange. Both spacecraft were slowing down ever so slightly more than the laws of gravity predicted. It was a tiny, persistent anomaly, a deceleration equivalent to a 10 billionth of the gravity you feel on Earth, but it was there. Over hundreds of millions of miles, this minuscule drag added up, pulling the Pioneers off course by thousands of miles. For years, this Pioneer anomaly fueled intense speculation. Had we stumbled upon a flaw in Einstein's theory of general relativity in the deep, quiet reaches of the solar system? Could it be the gravitational pull of unseen, dark matter concentrated near the Sun? Or was it evidence of some entirely new physical force, a whisper of unknown physics acting on our human-made objects? The mystery captivated physicists and the public alike, a tantalizing hint that our understanding might crack at the very edges of our own celestial neighborhood. The answer, when it finally came, was not a revolution in physics, but a masterclass in engineering humility. A meticulous, years-long effort led by a tireless team of scientists concluded that the culprit was heat, specifically thermal radiation pressure. The Pioneers were powered by radioactive plutonium pellets, whose decay generated heat to run their instruments. This heat radiated away from the spacecraft unevenly. More importantly, it reflected off the back of the spacecraft's large dish antenna. That gentle, photon-by-photon push from the spacecraft's own waste heat was acting like a tiny, constant brake, slowing the probes in exactly the way that had been observed. The case was closed with a detailed computer model that accounted for every watt of power and every surface's reflectivity. So why does this solved mystery belong on a list of cosmic puzzles? Because the Pioneer anomaly represents a crucial and humbling step in the scientific process. For over a decade, it stood as a genuine, data-driven challenge to our models of the cosmos. It forced scientists to consider extraordinary possibilities and to scrutinize every last detail of their assumptions. The ultimate solution required looking not out into the universe for dark forces, but inward at the spacecraft itself, at the subtle interplay of heat and light that had been overlooked. It reminds us that before we invoke new physics to explain a strangeness in the void, we must first exhaustively check for a leak in our own pocket of reality. The Pioneers' whisper was not a call from the darkness beyond, but an echo from their own warm metal hearts, teaching us that sometimes the greatest mysteries are the ones we build and launch ourselves. The solved whisper of the Pioneer probes taught us to look inward for answers, but another, more persistent whisper continues from much closer to home. This is the flyby anomaly, a tiny, unexplained hiccup in the speed of spacecraft that use Earth for a gravitational slingshot. To reach the outer planets, missions often perform a gravity assist, swinging close to our planet to steal a little of its orbital momentum and fling themselves deeper into space. The physics of this celestial billiard shot is exquisitely precise, calculated down to the millimeter per second. Yet on several occasions, our spacecraft have not followed the script. When the Galileo probe flew by Earth in 1990 and again in 1992, tracking stations detected a minute but real increase in its velocity that the equations did not predict. The same strange speed boost was later seen with the NEAR spacecraft heading to an asteroid and the Rosetta Comet chaser on its long journey. In each case, as the craft whipped around our planet, its velocity changed by just a few millimeters per second more than expected. The difference is vanishingly small, less than a fraction of a percent, but in the hyper-precise realm of orbital mechanics, it is a glaring error in the cosmic ledger. So what could possibly nudge a speeding spacecraft in the silent vacuum of near-Earth space? The mundane explanations were checked first. Could it be the drag of Earth's wispy outer atmosphere or pressure from the solar wind? Detailed models showed these forces were far too weak. Could it be an error in how we model Earth's gravity field or the subtle tidal pulls from the sun and moon? Again, the numbers did not add up. The anomaly seemed tied to the geometry of the flyby itself, appearing only during the closest approach. This led to more exotic, speculative ideas. One theory suggested it might be linked to Earth's rotation. Just as water swirling down a drain creates a drag, perhaps our planet's spinning mass energy somehow imparts an extra kick to passing objects, an effect too subtle for our current gravity equations. Others have wondered if it is a local clue to a larger mystery, like a faint halo of dark matter trapped by Earth's gravity, whose extra mass provides an unaccounted-for tug. The flyby anomaly remains an open case, a tiny fingerprint on our most precise machines suggesting that even in our own celestial backyard, a fundamental piece of the puzzle might still be missing. Every time we slingshot a probe toward the stars, we are not just testing its trajectory, but the very laws we believe govern its flight. Our universe is built on a foundation of precise numbers, a cosmic recipe written in the first few minutes after the Big Bang. In that searing, dense forge, the simplest atomic nuclei were forged from a soup of protons and neutrons. This process, called Big Bang nucleosynthesis, is one of the pillars of modern cosmology. The calculations are exquisite, predicting with stunning accuracy how much of the universe should be primordial hydrogen, the fuel for stars, and helium, the ash of that first fire. The predictions and our telescopic observations match almost perfectly, a triumphant confirmation of our model of the hot Big Bang. But there is one glaring exception, a single ingredient in the cosmic recipe that has stubbornly refused to align. The universe is missing its lithium. According to our best theories, the ancient clouds of gas that formed the first stars should contain about 3 times more lithium-7, the most common isotope of that element, than we actually find when we look. This is not a small rounding error, it is a factor of 3 discrepancy, a hole in our understanding of the universe's first moments. So where did all the lithium go? The puzzle splits cosmologists into different camps. One possibility is that our understanding of stellar physics is incomplete. Perhaps the oldest stars, which we observe to gauge the primordial abundances, are somehow destroying or diluting the lithium in their atmospheres over billions of years, hiding the true initial amount from our telescopes. Another avenue points to the nuclear physics itself. The rates at which protons and neutrons fuse to form lithium in that frantic early cauldron depend on incredibly precise measurements in particle accelerators. A slight revision to one of these poorly measured nuclear reaction rates could, in theory, bring the predictions back in line with observations. The most radical possibility, however, is that the error lies not in the stars or the nuclear data, but in our cosmology. What if the conditions in the first 3 minutes were not exactly as we have modeled? Could the presence of unknown particles or a slight variation in the density of the universe at that time have altered the nuclear chain reaction just enough to suppress lithium production? This tiny discrepancy on the periodic table is a crack in an otherwise solid story, a whisper from the dawn of time that we are still missing a fundamental piece of the narrative. The lithium problem forces us to question not just the stars we see, but the very furnace in which they were born. But if the lithium problem is a crack in the furnace of creation, the next mystery suggests the entire cosmic blueprint might be subtly tilted in our favor. It is called the axis of evil, and it is one of the most unsettling statistical glitches in modern cosmology. To understand it, we must look at the oldest light in the universe, the cosmic microwave background. This faint, cold glow is the afterimage of the Big Bang, a snapshot of the cosmos when it was just 380,000 years old, a searing plasma that had finally cooled enough for atoms to form and light to travel freely. This radiation fills the entire sky, a nearly perfect blackbody with tiny, millionth of a degree temperature fluctuations. These speckles are the seeds of all future structure, the slight over densities that would, over billions of years, collapse under gravity to form galaxies and clusters. According to our standard model, these fluctuations should be random, like a static snowstorm spread evenly across the sky with no preferred direction or alignment. They should have no correlation whatsoever with the much later arrangement of our local solar system. Yet, when scientists created exquisitely detailed maps of this ancient light from satellites like WMAP and Planck, they found something that sent a chill through the community. Certain large-scale patterns in the CMB, the very hills and valleys of the infant universe, appear to be weakly aligned with the plane of our solar system and the direction of Earth's motion through space. It is as if the universe's birth certificate has a faint watermark that points directly back to us. The statistical significance is the key. In a truly random, isotropic universe, the odds of such an alignment happening by pure chance are incredibly low, something like rolling a cosmic die and getting the same number a dozen times in a row. This correlation is so unexpected and philosophically troubling that it was dubbed the axis of evil, a name that reflects its challenge to the Copernican principle. That principle is a cornerstone of modern science, stating that we do not occupy a special or privileged place in the cosmos. The axis of evil whispers that maybe, in some bizarre way, we do. So what could explain it? The most conservative and likely answer is a systematic error. Perhaps some subtle contamination from our own galaxy's foreground light, or an unaccounted-for effect in the satellite's instrumentation, is imprinting this local signature onto the ancient signal. Scientists have hunted for these errors relentlessly. Another possibility is that it is a statistical fluke, a 1-in-1,000 coincidence that, in a universe with countless observers, was bound to show up somewhere, and we just happen to be the ones who see it. But the more radical interpretations are what keep cosmologists awake at night. Could it be that the fabric of space-time itself is not uniform, and our local region has a subtle, large-scale anisotropy that is affecting the light? Or, most mind-bending of all, does it hint that our entire observable universe is just one bubble in a vast, frothing multiverse, and the conditions of our local bubble are not perfectly random? The axis of evil remains an unresolved thorn in the side of cosmology. It is a reminder that our most cherished map of the universe's infancy might contain a shadow of ourselves, a ghost in the machine that either points to a profound flaw in our understanding or to the humbling possibility that we are, after all, somehow written into the cosmic background. That faint watermark on the cosmic background is a whisper of something strange, but out in the vast ocean of galaxies, we are caught in a current we cannot escape. Our entire Milky Way galaxy, along with its neighbors, is being pulled. We are not drifting aimlessly through the expansion. We are racing at over 2 million kilometers per hour toward a specific point in the darkness, toward a region of space so massive and mysterious it has earned a terrifying name, the Great Attractor. This is not a single object like a black hole, but a colossal gravitational anomaly, a concentration of mass so immense it bends the paths of entire galaxies for hundreds of millions of light-years around. Imagine a vast, invisible whirlpool in the cosmic sea, and we are caught in its flow along with thousands of other island universes, all streaming toward a hidden center we cannot see. For decades, this was a profound navigational puzzle. We knew we were moving toward the constellations Centaurus and Hydra, but when astronomers pointed their telescopes there, they saw not nearly enough. The visible galaxies in that direction did not account for the tremendous gravitational tug we felt. It was as if we were being pulled by a ghost continent lying just beyond the horizon. The core of the mystery lay in a simple cosmic accident of perspective. The direction of the Great Attractor happens to lie directly behind the crowded, dusty heart of our own Milky Way. This region is called the Zone of Avoidance, where the thick clouds of gas and stars in our galactic plane block our optical view, obscuring nearly 20% of the wider universe. It was the ultimate blind spot, hiding the very thing that was pulling us. For a long time, the Great Attractor was a map with a giant, frustrating blank spot right at the center of the action. The breakthrough came when we learned to see with new eyes. Optical light cannot penetrate the galactic dust, but longer wavelengths can. Radio waves, infrared light, and X-rays slip through the obscuring veil. Surveys using these tools began to sketch the hidden landscape. They revealed that the Great Attractor is not the ultimate destination, but rather a waypoint in a much larger journey. The pull we feel is part of an even vaster flow, a river of galaxies hundreds of millions of light years across, all streaming toward an incomprehensibly large concentration of mass known as the Shapley supercluster, the single greatest gathering of matter in our local universe. The Great Attractor itself appears to be a massive knot within this river, a supercluster of its own, but one that lies partly hidden behind our galaxy's dust. Modern missions like the European Space Agency's Gaia spacecraft are now bringing this hidden geography into sharp focus. By precisely mapping the positions and motions of over 1 billion stars in our own galaxy, Gaia helps us subtract the complex rotation of the Milky Way itself, allowing us to measure our true motion through intergalactic space with unprecedented accuracy. This refines our understanding of the pull, confirming the immense scale of the overdensity. The picture emerging is one of a cosmic watershed, where the gravity of these immense superclusters sculpts the large-scale flow of the universe. We are not being pulled toward a monster, but toward the deepest valley in the local gravitational landscape. The Great Attractor is a reminder that even as the universe expands, the ancient force of gravity is still writing the story on the largest scales, drawing galaxies together in a slow, stately dance toward the greatest concentrations of mass, most of which we now know remains frustratingly, powerfully dark. This immense gravitational current pulls us toward a hidden landscape, but it also begs a deeper question about our own cosmic address. Are we living in a particularly empty neighborhood of the universe? Mounting evidence suggests we might be residing inside a vast spherical bubble of relative nothingness known as the Keenan, Barger, Cowie void, or KBC void for short. This is not a perfect vacuum, of course, but a region of space hundreds of millions of light years across where the density of galaxies, clusters, and matter is significantly lower than the cosmic average. Think of the universe as a lumpy sponge with dense clusters and filaments of galaxies surrounding huge, empty cavities. According to some astronomers, our Milky Way is not on a filament or in a cluster wall, but floating near the center of one of the largest cavities ever observed. This idea emerges from a careful census of the galaxies around us. When we map the cosmos in 3 dimensions, measuring distances to thousands of galaxies, a pattern emerges. The distribution of matter appears to drop off as we look outward from our position, suggesting we are inside a giant underdense region. This has profound implications for one of the most critical numbers in cosmology, the Hubble constant. This constant measures the current rate of the universe's expansion. We can measure it locally by watching how fast nearby galaxies recede from us. We can also measure it from the far distance by studying the ancient light of the cosmic microwave background and calculating what the expansion rate should have evolved to by today. These two methods should give the same answer, but they do not. They disagree by a small but stubborn amount, a discrepancy known as the Hubble tension. The existence of the KBC void could be the key to resolving this tension. If we are sitting in a giant bubble of lower density, the gravity here is weaker. With less collective gravitational pull holding our local region together, galaxies on the edge of our void would be streaming outward into the denser surroundings faster than the true cosmic average. Our local measurement of the expansion rate would therefore be artificially high, like measuring the speed of a river from a position in a narrow, fast-moving channel, rather than from the wide, slow-moving basin. This would mean the Hubble tension is not a flaw in our fundamental physics, but a correction needed for our unrepresentative viewpoint. The implications are philosophically jarring. It would mean we do, in fact, live in a special place, a cosmic backwater of unusual sparseness. This directly challenges the Copernican principle, the bedrock assumption that our position in the universe is not privileged or unique. We have always assumed we are typical observers in a typical region. The KBC void suggests we might be cosmic outliers, living in a quiet bubble whose emptiness skews our perception of the entire cosmos. Not all astronomers are convinced the void is real or large enough to explain the data. The debate is fierce because accepting it forces us to rewrite the story of our place in the universe. Are we truly at the center of a great cosmic nothing, our measurements distorted by the local emptiness? Or is this another statistical illusion in the grand map of creation? The answer will determine whether we see the universe clearly or through a lens of our own exceptional emptiness. The quiet bubble we might inhabit could be warping our most fundamental measurement of the cosmos, a measurement now at the heart of a crisis. This is the Hubble tension, and it is not a minor academic disagreement. It is a direct, stubborn clash between two ways of seeing the universe, and the discrepancy is growing sharper with every new, precise observation. On one side, we have the local universe. Astronomers use cosmic lighthouses called Cepheids variable stars and type Ia supernova. Cepheids pulse with a rhythm directly tied to their true brightness. By measuring their pulse rate and how dim they appear from Earth, we can calculate their exact distance with remarkable accuracy. Type Ia supernova are even brighter standard candles, exploding with a consistent peak brightness. By charting these beacons in relatively nearby galaxies, we can measure how fast those galaxies are receding from us and calculate the current expansion rate, known as the Hubble constant. The result is a precise, modern speedometer for the cosmos. On the other side, we look back to the universe's infancy. The Planck satellite mapped the cosmic microwave background, that fossil light from when the universe was only 380,000 years old. By analyzing the subtle patterns in that ancient glow, scientists can deduce the universe's ingredients, the amounts of ordinary matter, and dark energy, and run the cosmic film forward in time. Using our well-tested model of cosmology, they can predict what the expansion rate should be today. These two methods, one a direct local measurement and the other a backward-looking prediction, should meet at the same number. They do not. The local measurement gives a faster expansion rate. The early universe prediction gives a slower one. The difference is about 10%, a gap that persists even after accounting for every known source of error. It is as if you carefully calculated how fast a car should be going based on its engine specs and the road conditions. But when you point a radar gun at it, the reading is consistently, undeniably higher. This tension is not fading away, it is tightening. New observations with the Hubble Space Telescope and the James Webb Space Telescope have only confirmed the local measurements, ruling out many potential instrumental errors. The crisis is real, so what could be causing this rift in our cosmic understanding? One compelling idea is the existence of early dark energy. Our standard model assumes dark energy, the force accelerating expansion, has been constant or very slowly changing. But what if, in the universe's first few 100,000 years, there was an extra burst of this repulsive energy? This early dark energy would have subtly changed how sound waves propagated in the primordial plasma, leaving a faint imprint on the cosmic microwave background that would, in turn, alter the predicted expansion rate for today. Adding this ingredient could potentially bring the two numbers into alignment, suggesting the cosmos had a more dynamic youth than we thought. Another possibility involves ghostly particles streaming through everything. Neutrinos are nearly massless particles that rarely interact with matter. We know they have some tiny mass, but what if there are additional, sterile types of neutrinos we have not yet detected with slightly different properties? These extra relativistic particles in the early universe would change the timing of key events, like when matter and radiation decoupled, again tweaking the prediction from the ancient light. The Hubble tension forces us to ask if we are missing a fundamental component in our cosmic recipe book, an ingredient that was more important in the past than it is now. It is a direct challenge to our standard model of cosmology, a signal that our elegant story of the universe might require a surprising new chapter. The disagreement between then and now is not just a number, it is a message from the depths of time, telling us our map of reality is still incomplete. That tension between our local measurements and the ancient past speaks to a universe hiding its true contents, not just in dark forms but in plain sight. For decades, cosmologists faced a startling accounting problem with the very stuff we are made of. Our best models of the Big Bang tell us precisely how much ordinary atomic matter, protons and neutrons, collectively called baryons, should exist in the cosmos. This is the matter that forms every star, planet, and human being. Yet when we added up all the baryons we could actually see in stars, galaxies, and the cool gas in between, we came up short by a staggering 30 to 40%. Half the atoms in the universe were simply missing. This was the missing baryon problem, a glaring hole in our inventory of reality. It was not dark matter, which is something else entirely, but regular atoms that had seemingly vanished from the cosmic ledger. So where did they go? The leading suspect for years has been a ghostly structure known as the warm-hot intergalactic medium, or WIM. Picture the large-scale structure of the universe not as isolated galaxies floating in blackness, but as a vast, intricate cosmic web. Gravity, over billions of years, has drawn matter into an immense network of filaments, like the delicate threads of a spider's web, connecting massive galaxy clusters at the nodes. Theorists predicted that the missing baryons did not collapse into galaxies, but instead settled into these filaments, forming a diffuse ocean of incredibly hot, ionized gas. This gas is so tenuous, perhaps just a few atoms per cubic meter, and so blisteringly hot at hundreds of thousands to millions of degrees that it is virtually invisible to traditional telescopes. It does not glow in optical light. It does not form cool, detectable clouds. It is the universe's hidden plumbing, a faint, steaming mist woven through the voids. Detecting this WIM has been a monumental challenge, requiring us to look at the universe in a very specific way. Since the hot gas is ionized, it can absorb very specific wavelengths of far ultraviolet and soft X-ray light. The strategy is to use brilliant, distant beacons called quasars as cosmic flashlights. As their intense light travels billions of light years through the cosmic web to reach us, it passes through these filaments. Atoms within the WIM, like oxygen and neon heated to extreme temperatures, imprint faint absorption lines on the quasar's spectrum, like a chemical fingerprint left on the light. It is an incredibly subtle signal, a whisper of a shadow against an already distant and brilliant source. Another method is to look for the faint, diffuse X-ray glow that the hottest parts of these filaments might emit, a soft background sizzle across the sky. Recent years have brought breakthroughs by combining data from multiple X-ray and ultraviolet observatories and carefully stacking the signals from many quasar sightlines. Astronomers have begun to find these fingerprints. They have detected the telltale signatures of highly ionized oxygen in the spaces between galaxies, tracing the long-sought filaments of the cosmic web. The evidence is mounting that we have finally found the universe's missing atoms, not in glorious galaxies, but in this vast, hot, intergalactic fog. The solution transforms our view of the cosmos. We do not live in a universe of isolated islands, but within a continuous, seething ocean of matter, most of which exists in a form so elusive it took us half a century to prove it was there. The ordinary has been hiding in the most extraordinary places all along. Yet the searing hot filaments of the cosmic web are not the only invisible rivers flowing through the void. From the deepest reaches of intergalactic space, atomic bullets are screaming into our atmosphere, carrying with them energies that defy belief. These are ultra-high-energy cosmic rays, and they are the most energetic particles ever observed in nature. A single one of these subatomic projectiles, often a proton or an atomic nucleus, can carry the kinetic energy of a professionally thrown baseball, all compressed into a speck smaller than an atom. That is millions of times more energy than we can produce in our most powerful human-made particle accelerators like the Large Hadron Collider. They arrive at the top of our atmosphere at nearly the speed of light, a relentless, silent rain of the universe's most extreme ammunition. And for over a century since their discovery, their origin has been one of astrophysics' most enduring puzzles. Where in the cosmos are these unimaginable particle accelerators? The challenge of finding their source is twofold. First, cosmic rays are charged particles. This means that as they travel across millions of light years, the magnetic fields that thread through galaxies and intergalactic space bend their paths, scattering them like pinballs. By the time one reaches Earth, its incoming direction points back not to its birthplace, but to the last magnetic curve in its journey. It is like trying to find the source of a river by following a single wind-blown leaf. Second, the universe itself should theoretically prevent such particles from traveling vast distances. This is due to a concept called the GZK cutoff, named for physicists Greisen, Zatsepin, and Kuzmin. They realized that a proton with ultra-high energy, barreling through the sea of cosmic microwave background radiation, should constantly collide with the low-energy photons of that ancient light. Each collision would sap the proton's energy like a marathon runner constantly tripping over tiny hurdles. Over a distance of about 150 million light-years, even the most energetic proton should be slowed below a certain threshold. This creates a cosmic horizon. Any ultra-high-energy cosmic ray we detect must therefore come from within our local cosmic neighborhood, within a volume of space that contains relatively few galaxies. Yet within that volume we see no obvious cataclysmic source pointing directly at us. This is where the great hunt begins. To detect these rare particles, we do not catch them directly. When an ultra-high-energy cosmic ray strikes the atmosphere, it creates a spectacular cascade. It smashes into an air molecule, creating a shower of secondary particles that in turn create more, resulting in a vast, expanding disk of billions of particles and a flash of faint ultraviolet light called fluorescence, all raining down over several square miles. Observatories like the Pierre Auger Observatory in Argentina are built to capture this aftermath. It covers an area the size of Rhode Island with over 1,600 water tanks that detect the particles as they hit the ground, and 24 telescopes that watch the night sky for the faint fluorescence glow of the shower developing overhead. By combining these two views, scientists can reconstruct the energy and the rough incoming direction of the original cosmic ray with remarkable precision. The data has brought us clues, but not a verdict. The arrivals are not perfectly random. They show a weak correlation with the locations of nearby active galactic nuclei. the violent cores of galaxies where supermassive black holes are devouring matter and spewing out jets of radiation. Other possible sources include ferocious star-forming galaxies, or perhaps even more exotic engines like giant magnetic flares from collapsing neutron stars. Yet no single source type has emerged as the definitive answer. Each ultra-high-energy event is a cryptic postcard from a cosmic catastrophe, its return address smudged by magnetic fields, its message written in the language of a particle shower. We are left staring at the aftermath of the universe's most powerful explosions, trying to decipher the signature of the trigger from the scattered debris that lands in our fields. These atomic bullets from cosmic catastrophes arrive as a steady, if mysterious, rain, but the universe also speaks in sudden, deafening shouts. Without warning, a point in the sky can erupt with more energy in a single millisecond than our sun releases in 3 entire days. This is a fast radio burst, a flash of radio waves so intense it can outshine an entire galaxy for a fleeting instant, only to vanish back into the silent dark. The first one was discovered in 2007, buried in archived data from the Parkes Radio Telescope in Australia. For years, it was considered a possible glitch, an anomaly so bizarre that some astronomers jokingly blamed it on microwave ovens in the observatory's kitchen. But then more were found, each a solitary, brilliant spike in the data, tracing a line across millions or even billions of light years to reach us. The sheer power involved is almost incomprehensible. To be detectable across such cosmic distances, the source must be releasing as much energy as hundreds of millions of suns, all focused into a radio frequency blast lasting less time than the blink of an eye. It is like hearing a thunderclap from another galaxy. The mystery deepened with a pivotal discovery in 2016. While most FRBs were one-off events, a single source was caught repeating, sending out multiple bursts from the same patch of sky. This proved they were not just the final, catastrophic death cries of some object, but could be produced by something that survived the event, something that could fire again and again. Suddenly, the hunt was on to pinpoint where these cosmic sirens were coming from. The breakthrough came from a new generation of telescopes, like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. With its vast, stationary array of metal mesh, CHIME acts like a cosmic surveillance camera, monitoring a huge swath of the sky at once. It began catching FRBs by the dozens, sometimes multiple in a single day. By using networks of telescopes across continents to perform very long, baseline interferometry, astronomers achieved a feat of cosmic triangulation, tracing repeating bursts back to their home galaxies. They were not coming from the empty void, but from the spiral arms of distant, ordinary galaxies, locations where young, massive stars live and die. This pointed squarely to one of the leading suspects, magnetters. A magnetter is a type of neutron star, the collapsed city-sized core of a giant star that exploded as a supernova. What sets a magnetter apart is its unimaginably powerful magnetic field, trillions of times stronger than Earth. This field is under such immense stress that it can occasionally snap and reconfigure in a starquake, a seismic event on the stellar surface that could, in theory, release a titanic pulse of radio waves. Observations have since strengthened this link, with telescopes catching an extremely powerful radio burst from a known magnetter within our own Milky Way, proving that at least some FRBs can be made by these magnetic monsters. Yet the story is not so simple. The energies of the most extreme extragalactic bursts still push the limits of what a magnetter starquake might produce. Other theories remain on the table, involving the chaotic mergers of neutron stars or the violent accretion disks of black holes. And yes, the possibility of an artificial origin, a beacon or propulsion signature from an advanced civilization, has been entertained with scientific seriousness, though it remains the least likely explanation in the absence of any patterned informational signal. The true fascination of FRBs lies in their duality. They are both a solved puzzle and an open frontier. We have likely identified one of the culprits, yet the sheer variety of bursts, their different energies and patterns, suggests we are hearing more than one phenomenon. Each millisecond flash is a postcard from a realm of extreme physics, a snapshot of magnetic fields twisting beyond breaking or dense bodies colliding in the dark, delivering a message written in pure energy that crosses the cosmos just to fade on our receivers. The universe's fleeting shouts may find their source in magnetars, but one singular whisper from the void has echoed for decades without any answer at all. It remains the most tantalizing, unresolved event in the history of the search for extraterrestrial intelligence, known forever by the exclamation scrawled beside it, the wow signal. In the summer of 1977, a radio telescope at Ohio State University known as the Big Ear was engaged in a routine sky survey, listening for any narrowband radio signal that might stand out from the natural cosmic noise. Such a signal, focused on one specific frequency, would be a potential technological fingerprint, as natural astrophysical processes tend to broadcast across a wide spectrum. On the night of August 15th, the telescope's automated system recorded a 72-second burst of intense radiation. It was a perfect narrowband signal, precisely at the frequency of the hydrogen line, a logical channel for any civilization wanting to be noticed. The signal rose and fell in exactly the way a star would as it drifted through the telescope's fixed field of view, a perfect match for an extraterrestrial beacon. The next day, astronomer Jerry Amon was reviewing the computer printout, a long sheet of paper with columns of letters and numbers representing signal strength. One sequence leapt out, 6 characters reading 6EQUJ5. In the system used, letters represented values from 10 upward, so this sequence meant a signal strength of 10, 15, 26, 30, 19, 10. It was an enormous spike. Amon circled the sequence in red pen and in the margin wrote a single emphatic word. Wow, the signal had all the hallmarks everyone was looking for, but it was never heard again. Despite repeated and dedicated efforts to find it over the years, using more powerful equipment pointed at the same patch of sky in the constellation Sagittarius, the silence has been absolute. The debate over its origin has never ceased. Could it have been a human-made transmission, perhaps a secret military satellite or a reflection from space debris? The frequency was supposed to be protected for astronomy, and the signal's characteristics do not match any known human technology of the time. Could it have been a natural astrophysical event like a comet's radio emission? Detailed analyses have ruled out the comets that were in the area at the time. The possibility that it was a one-time interstellar flare from a distant civilization, a lighthouse beam that swept over Earth and then moved on, remains the most haunting explanation. The WOW signal stands alone, a single, perfect candidate in a desert of cosmic static. It is a ghost in the data, a 72-second suggestion that we might not be alone, followed by 47 years of profound silence. It taught us that the universe might speak only once, and if you are not listening at exactly the right moment, the conversation is over before it even begins. While the WOW signal was a fleeting whisper, another star began screaming for attention with its light. In the constellation Cygnus, a seemingly ordinary star named KIC 8462852, now better known as Tabby's star or Boyajian star, began behaving in a way no one had ever seen. Citizen scientists from the Planet Hunters project, sifting through data from NASA's Kepler Space Telescope, flagged it as deeply strange. Kepler's mission was to find exoplanets by watching for the telltale, periodic dimming that occurs when a planet transits or passes in front of its host star. These dips are usually small, predictable, and symmetrical. Tabby's star shattered that pattern entirely. Its light did not dip by a tidy fraction of a percent. Instead, it plunged by up to 22% at irregular, unpredictable intervals, and the shapes of the dips were jagged and asymmetrical. It was as if something enormous, complex, and utterly chaotic was repeatedly blocking its light. The strangeness demanded an extraordinary explanation, and for a moment, the most thrilling one seemed possible. Could we be seeing the shadows of an alien megastructure? The hypothesis, proposed seriously by astronomers like Jason Wright, suggested a vast swarm of solar collectors, a Dyson swarm under construction, orbiting the star and intermittently blocking its light in these bizarre, non-repeating patterns. It was a concept straight out of science fiction, and for a while it captured the public imagination, turning this obscure star into a global sensation. Yet science thrives on testing even the most exciting ideas. Further observations across multiple wavelengths told a different, though still fascinating, story. When the star dimmed in visible light, it dimmed less in infrared light. This fingerprint is crucial because solid objects like planets or megastructures block all wavelengths equally. Dust, however, behaves differently. Tiny dust grains are better at blocking shorter wavelength blue and visible light, while allowing longer wavelength infrared light to pass through more easily. The data pointed squarely to circumstellar dust, a vast, uneven cloud of fine particles orbiting the star in a complex and clumpy disk. But this was no ordinary debris disk. The scale and irregularity of the dimming event suggest something catastrophic and recent, perhaps a collision between planets or the breakup of a massive comet swarm, creating a chaotic shroud of debris that has not yet settled into a stable ring. This dust cloud explanation is now the leading one, but it does not make Tabby's star any less of a mystery. The star itself also exhibits a long-term, gradual dimming over the century of historical records, which is harder to explain with dust alone. The complete picture remains elusive. We are likely witnessing the aftermath of a cosmic demolition derby, a messy, violent event that has shrouded a star in its own wreckage, casting deep and ragged shadows across hundreds of light years. It is a reminder that while the answer may not be aliens, the universe is still capable of engineering phenomena so bizarre they momentarily stretch our imagination to its limits. Tabby's star is a monument to cosmic chaos, but its strange dimming lights point to a deeper, more profound silence. If the universe is so vast and ancient, brimming with hundreds of billions of stars in our galaxy alone, many older than our sun, then where are all the other builders? This is the essence of the Fermi Paradox, the startling contradiction between the high probability of extraterrestrial civilizations and the utter lack of evidence that they exist. Physicist Enrico Fermi posed it bluntly over lunch in 1950, asking simply, "Where is everybody?" The logic is compelling. Our Milky Way is about 13.6 billion years old. Our solar system is only 4.6 billion years old. That means there were billions of years before Earth even formed for other star systems to give rise to life, intelligence, and technology. Even at a small fraction of the speed of light, a civilization with modest interstellar travel could have colonized the entire galaxy within a few tens of millions of years, a mere blink in cosmic time. Their probes, their signals, or their engineering should be everywhere. Yet we look out and hear only a cosmic quiet, a silence so deep it echoes. To frame the problem, astronomer Frank Drake created his famous equation, a way to estimate the number of communicating civilizations in our galaxy. It multiplies factors like the rate of star formation, the fraction of stars with planets, the number of habitable worlds per system, the fraction where life actually emerges, the fraction where life becomes intelligent, the fraction that develops detectable technology, and finally, the length of time such a civilization broadcasts signals into space. The equation is not meant to give a single answer, but to show where our ignorance lies. We can plug in optimistic numbers and get a galaxy teeming with voices. We can use pessimistic numbers and find ourselves utterly alone. The terrifying beauty of the paradox is that every term in that equation is a potential wall, a filter that might stop life's progress dead. This leads to one of the most unsettling solutions, the concept of the great filter. The idea is that somewhere between the inert chemistry of a primordial planet and the emergence of a galaxy-spanning civilization, there is at least one step that is incredibly, vanishingly unlikely. It is a bottleneck that almost all life fails to pass. The haunting question is, where in that timeline does the filter lie? Is it behind us? Are we miraculously lucky that simple life arose on Earth, or that single-celled organisms made the leap to complex, multicellular life? If the filter is in our past, it means the hardest steps are over, and the path to intelligence might be open, making a silent galaxy even more puzzling. Or more frighteningly, is the great filter ahead of us? Is it something that inevitably destroys technological civilizations before they can spread, like self-destruction through war, ecological collapse, or a dangerous technological discovery? If that is the case, then our own future may hold a silent, universal deadline. Other solutions offer different kinds of solitude. The zoo hypothesis suggests we are in a kind of cosmic wildlife preserve, that advanced civilizations are aware of us but have chosen not to interfere, observing from a distance until we reach a certain maturity. The planetarium hypothesis is even more introspective, proposing that what we perceive as the universe is a sophisticated simulation or illusion, and the silence is simply a feature of the program. There is also the possibility that intelligence itself is not an evolutionary advantage, or that technological civilizations are so fleeting, burning bright for only a few centuries before fading, that the odds of two overlapping in both time and space are astronomically small. The Fermi Paradox holds up a mirror to our own existence. It forces us to confront whether we are a breathtakingly rare fluke, a lonely spark in an endless night, or whether the silence is a warning, a sign that the universe is far more dangerous for thinking beings than we have dared to imagine. Every silent star we look upon is now a question, and the answer will define our place in the cosmos forever. That profound silence among the stars forces us to question the very nature of reality, a question that reaches its ultimate extreme at the edge of a black hole. Here, in the warped space-time surrounding these cosmic pits, our two most successful theories of physics enter a direct and violent conflict. This is the black hole information paradox, and it threatens to unravel our understanding of the universe at its most fundamental level. The paradox begins with a simple principle from quantum mechanics, the rules governing the subatomic world. In quantum theory, information is never destroyed. It might be scrambled, transformed, or hidden, but it is fundamentally conserved. If you could know the exact quantum state of every particle in a burning log, you could, in principle, reverse the process and reconstruct the log from the smoke and ash. The information about what made the log is always preserved in some form. Now, bring a black hole into the picture. According to Albert Einstein's theory of general relativity, a black hole's boundary, the event horizon, is a point of no return. Anything that crosses it, whether a spaceship, a star, or a single particle of light, is lost forever to the outside universe. The black hole is defined only by its mass, its spin, and its electric charge. This is the no-hair theorem, suggesting black holes are the ultimate simple objects. If you throw a grand piano, a hard drive full of data, and a barrel of confetti into a black hole from the outside, they all become indistinguishable, adding only to the black hole's mass. The specific, intricate information about what fell in seems to be erased from reality. This was the status quo until Stephen Hawking made a revolutionary discovery in the 1970s. He showed that black holes are not completely black. Due to quantum effects at the very edge of the event horizon, they should slowly radiate away energy, emitting a faint glow of particles now called Hawking radiation. This radiation causes the black hole to lose mass and, over astronomical timescales, completely evaporate. And here lies the heart of the paradox. Hawking's original calculations indicated that this radiation is purely thermal, like the glow from a hot stove. It contains no information about what fell into the black hole. So, imagine that grand piano falls in. The black hole eventually evaporates, leaving behind only this random, featureless thermal radiation. The intricate quantum information that described the piano's wood grain, its strings, its shape, has seemingly vanished from the universe. This violates the sacred rule of quantum mechanics. It presents science with a stark choice. Either quantum mechanics is wrong and information can be destroyed, or general relativity is wrong and something must happen to preserve the information. For decades, this was the greatest unsolved problem in theoretical physics. The modern resolution, which is still being fiercely debated, involves some of the most mind-bending concepts in science. One leading idea comes from the holographic principle. This suggests that all the information contained within a three-dimensional volume of space, like the interior of a black hole, is actually encoded on its two-dimensional boundary, the event horizon. Think of it like a cosmic barcode. When the piano falls in, its information isn't destroyed, but is smeared and stored across the surface area of the black hole in Planck-scale pixels. As the black hole evaporates via Hawking radiation, this encoded information is slowly and chaotically leaked back out into the universe through subtle correlations in the radiation. The radiation is not random after all. It carries a scrambled, nearly indecipherable story of everything that fell in. Another, more radical proposal is the firewall hypothesis. If information must escape, perhaps the event horizon is not a smooth, empty space as relativity predicts, but a searing wall of high-energy particles, a literal firewall that incinerates anything crossing it. This would preserve information by preventing anything from actually entering the black hole in the first place, but it would violently contradict Einstein's picture of an uneventful fall through the horizon. The debate continues, with physicists using mathematical tools from string theory and quantum gravity to probe this impossible boundary. The black hole information paradox is more than an abstract puzzle. It is a direct probe into how the universe handles its own deepest secrets, forcing us to invent a new physics that can reconcile the very large with the very small. The profound silence of the cosmos is not a permanent condition, but a prelude to an ending we can only predict. Our universe is not static, it is a story with a final chapter, and the nature of that ending depends entirely on the true character of the mysterious dark energy currently accelerating everything apart. The leading and most haunting forecast is called the heat death or big freeze. In this scenario, dark energy remains a constant, gentle pressure. The expansion continues to accelerate forever. Over trillions of years, galaxies beyond our local group will vanish over the cosmic horizon, their light stretched beyond detection. Within each galaxy, star formation will eventually cease as all interstellar gas is used up or expelled. Existing stars will burn out one by one, leaving behind cold stellar remnants, black dwarfs, neutron stars, and black holes. Even these will not last forever. Over timescales so vast they make the current age of the universe seem like a single heartbeat. Black holes themselves will evaporate via Hawking radiation, dissolving into a faint mist of particles. The universe will become an ever-cooling, ever-expanding sea of dilute radiation and isolated particles, where the temperature approaches absolute zero and no further work can be done. It is a quiet, fading end, a universe dying not with a bang, but in an infinite, deepening whisper of cold and dark. But there is a far more violent alternative, the Big Rip. This fate emerges if dark energy is not constant, but instead grows stronger over time, a force called phantom energy. In this terrifying model, the repulsive force of dark energy would eventually overcome every binding force in nature. First, the acceleration would tear apart galaxy clusters, then individual galaxies. As the force intensifies, stars would be ripped from their orbits. In the final months, planetary systems would be shredded. In the last minutes, stars and planets themselves would be torn asunder. In the final, catastrophic instance, atoms would be ripped apart, then atomic nuclei, and finally the very fabric of space-time itself would be sundered. The universe would end in a singular, violent rupture of reality. These are the two dominant fates driven by dark energy's continued dominance. Yet other endings linger in the realm of possibility, requiring a dramatic shift in the cosmic balance. One is the classic Big Crunch, a reversal of the Big Bang. For this to happen, the density of matter in the universe would need to be high enough that gravity eventually halts and reverses the expansion. All of space would begin to collapse back in on itself. Galaxies would merge, temperatures would soar, and the universe would contract toward an infinitely hot, dense singularity, perhaps setting the stage for another Big Bang in a cyclical universe. Current observations of accelerating expansion strongly disfavor this outcome, but it remains a theoretical bookend. That idea of a cyclical universe is itself a compelling alternative, a cosmos with no true beginning or end, but an eternal sequence of bangs and crunches, or collisions between higher dimensional brains in string theory. Our fate, therefore, is written in the subtle behavior of a force we cannot directly see. To read it, astronomers are engaged in a monumental forensic project. They are building ever more precise maps of the universe's expansion history, using distant supernova, baryon acoustic oscillations frozen into the galaxy distribution, and gravitational lensing to measure how the acceleration rate has changed over billions of years. Is it perfectly constant, as the cosmological constant suggests, pointing toward the Big Freeze? Or is it slowly increasing, the signature of phantom energy and a future Big Rip? The answer lies in the painstaking measurement of dark energy's equation of state, a single number that describes its pressure and density, each new observatory from the Vera Sea. Rubin Observatory to the Nancy Grace Roman Space Telescope is designed to tighten the constraints on this number, to peer deeper into the future by examining the past. We are, in a very real sense, taking the universe's vital signs to diagnose its ultimate destiny. The conclusion is both humbling and awe-inspiring. The final act of our cosmic story is not yet written, and we are the first generation capable of reading the opening lines. Our universe's ultimate fate hinges on forces we can barely measure, but its very fabric might be built from something far stranger than empty space. At the smallest imaginable scales, a trillionth of the size of an atomic nucleus, the smooth, continuous stage upon which cosmic dramas play out may dissolve into a seething, chaotic froth. This is the quantum nature of space-time, the question of whether the dimensions of length, width, and depth, and the flow of time itself, are fundamentally smooth like a calm sea or granular like a fine, shimmering sand. The conflict arises from the two pillars of modern physics. Quantum mechanics describes a fuzzy, probabilistic world of particles and forces, while Einstein's general relativity paints gravity as the elegant curvature of a smooth spacetime continuum. These theories work flawlessly in their own domains, but they become mathematically incoherent when forced together, particularly in the extreme conditions of a black hole's singularity or the first instant of the Big Bang. To resolve this, physicists propose that spacetime itself must be quantized, broken into discrete, indivisible units at the Planck scale. Think of it this way: a digital photograph looks smooth from a distance, but zoom in far enough and you see it is made of individual pixels. Our reality might be pixelated in a similar, unimaginably fine way. Two leading frameworks attempt to paint this pixelated picture. Loop quantum gravity suggests that space is woven from a network of tiny, one-dimensional loops like an inconceivably fine mesh. These loops connect at nodes, creating a fabric where area and volume come in specific, quantized amounts, not a smooth continuum. In this view, the Big Bang might not have been a singularity, but a big bounce where a previous universe collapsed and then rebounded into our own. String theory, on the other hand, proposes that the fundamental units are not point particles but vibrating, multidimensional strings. The different vibrations of these strings correspond to different particles and forces. Crucially, string theory requires more than the 3 spatial dimensions we experience, suggesting 6 or 7 extra dimensions curled up into a space so small we never notice them. In this framework, gravity emerges naturally from the vibrations of a particular type of string, offering a potential unified theory of everything. The challenge, and the reason this remains a profound mystery, is that testing these ideas seems almost impossibly beyond our reach. The Planck length, where these quantum effects should dominate, is about 10 to the negative 35 meters. To probe that scale directly with a particle accelerator, we would need a machine larger than our entire solar system, powered by more energy than exists in our galaxy. So we search for indirect clues, for cosmic fingerprints of this foamy spacetime. One possibility is that this quantum graininess could subtly alter the speed of light over vast distances. A high-energy gamma-ray photon traveling for billions of years might arrive at our telescopes a fraction of a second later than a lower-energy photon from the same burst if it had to navigate a bumpy quantum terrain. Astronomers scour the data from gamma-ray bursts and distant active galaxies for this telltale lag, but so far the evidence remains elusive. Another avenue is to look for the faint imprint of primordial gravitational waves, ripples in spacetime from the universe's violent birth on the cosmic microwave background. The specific pattern of these waves could reveal details about the universe's quantum state in its first moments, potentially favoring one theory over another. We are, in essence, trying to hear the whisper of spacetime's atomic structure in the echo of the Big Bang, a task of staggering difficulty. The quantum nature of spacetime is the ultimate frontier of physics, a mystery that asks what reality is made of at its core. We are left with beautiful, mathematically elegant theories describing a world of loops, strings, and hidden dimensions, a cosmos far more alien and intricate than it appears, waiting for a genius or an experiment to reveal its true granular face. That granular fabric of spacetime might hide an even more elusive quarry, a particle so fundamental it has never been seen. Every magnet you have ever held tells a story of duality. Break a bar magnet in half, and you do not get an isolated North Pole and an isolated South Pole. Instead, you create 2 new, smaller magnets, each with its own inseparable north and south. This is the law of magnetic dipoles, a rule so consistent it seems written into the universe. Yet, our most ambitious theories of physics insist that isolated magnetic charges, called magnetic monopoles, should exist. They would be the magnetic equivalent of an electric charge, a particle that is pure north or pure south. Their absence is not just a curiosity, it is a glaring problem that once threatened to unravel our entire picture of the early cosmos, and its solution gave us one of the most compelling arguments for a breathtaking cosmic event: inflation. The need for monopoles comes from grand unified theories. These are attempts to describe the universe's fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force, as different facets of a single super force that existed in the extreme heat of the first moments after the Big Bang. As the universe expanded and cooled, this unified force is thought to have undergone phase transitions, splitting into the distinct forces we see today, much like steam condensing into water droplets. In many of these theories, these cosmic cracks in the symmetry of the early universe would have created topological defects, stable knots in the fabric of reality. Magnetic monopoles are predicted to be one such defect: incredibly massive particles that should have been produced in staggering numbers, as abundant as protons. If that were true, their immense mass would have dominated the density of the universe, causing it to collapse long before stars or galaxies could ever form. The fact that we exist in a universe that is billions of years old and filled with structure is direct observational proof that these monopoles are nowhere to be found. We have searched for them with painstaking experiments, using sensitive loops of superconducting wire, waiting for the telltale jump in current that would signal a single north or south pole passing through. The silence from these detectors is deafening. So where did all the monopoles go? The most elegant answer is a concept called cosmic inflation. This theory proposes that a fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion, doubling in size over and over again in a span of time far shorter than the blink of an eye. This inflationary burst would have been driven by a strange, repulsive energy field that temporarily dominated everything. The effect on those pesky monopoles would have been dramatic. Imagine a tiny, dense patch of the early universe containing a huge number of monopoles like confetti packed into a thimble. Now, inflate that thimble to the size of our entire observable universe in an instant. The confetti, our monopoles, would be diluted to such an extreme degree that you would be lucky to find even one in the entire volume we can see. Inflation doesn't destroy them, it simply spreads them so thin they become effectively undetectable, solving the monopole problem in one sweeping gesture. This dilution is so powerful that it also explains other cosmic puzzles, like why the universe appears so uniform in all directions. The magnetic monopole, a particle we have never seen, thus became a key piece of evidence for an event we can never directly observe. Its absence speaks volumes, a ghostly fingerprint of the universe's most violent and transformative growth spurt, a silent witness to the moment everything changed. This incredible smoothness is the very thing that now poses a deep and troubling question. Look in any direction, and the temperature of the cosmic microwave background is the same too within a tiny fraction of a degree. This uniform warmth is the thermal echo of the Big Bang, a final, even heat after the primordial fire. But here is the puzzle: the universe is not old enough for this to make sense. In the standard Big Bang model, there simply has not been enough time for light or heat to travel from one side of the observable universe to the other. The cosmos expanded at a stately pace, meaning that regions on opposite horizons today were never in causal contact. They were like islands in an ocean that had never exchanged a single drop of water or a single photon of warmth. Yet mysteriously, they have reached the exact same temperature. How could these separate, disconnected parts of the universe have coordinated so perfectly? This is the horizon problem, a paradox that suggests our early universe must have been in thermal contact somehow, that it must have been much smaller and more connected than the standard story allows. The leading and most elegant solution is a breathtaking concept: cosmic inflation. This theory proposes that a tiny fraction of a second after the initial singularity, the universe was seized by a strange, repulsive energy field. For a fleeting instant, perhaps just 1/trillionth of a trillionth of a trillionth of a second, space itself expanded at an exponential, faster-than-light rate. It was not matter moving through space, but the fabric of space-time itself stretching at an unimaginable pace. In that blink, a subatomic speck of the primordial universe inflated to a size larger than our entire observable cosmos today. This radical growth spurt solves the horizon problem beautifully. Before inflation, the entire region that would become our universe was microscopic, tiny enough for every part to be in intimate thermal contact, exchanging heat and energy until it reached a perfectly even temperature. Then inflation happened, taking that small, smooth, uniform patch and stretching it to cosmic proportions, preserving that smoothness across the vast expanse we see today. It is like taking a single, perfectly mixed drop of dye and stretching it to fill an entire swimming pool. The color remains uniform throughout. This process also explains the universe's remarkable flatness and the absence of those troublesome magnetic monopoles, diluting them to near nothingness. While we cannot see inflation directly, its predictions have been spectacularly confirmed. It precisely accounts for the specific pattern of tiny temperature fluctuations we see in the cosmic microwave background, the seeds that gravity would later sculpt into galaxies. Inflation paints a picture of a cosmic genesis far more violent and transformative than a simple explosion, a moment when the very rules of reality were rewritten to create the smooth, vast, and strangely coherent stage we now call home. This perfect smoothness is mirrored by another, equally precise cosmic alignment. The very shape of space itself, the geometry of the entire universe, appears to be perfectly flat. This is not flat like a table, but flat in the sense that the rules of geometry we learned in school, Euclid's geometry, hold true on the largest scales. In a flat universe, parallel lines never meet, and the angles of a triangle always add up to exactly 180 degrees. This flatness is not just a curious fact, it is a condition so precise and so unstable that its existence today defies all reasonable odds, pointing directly to a moment of profound cosmic fine-tuning. To understand why, we must consider the other possibilities. General relativity tells us that the fabric of the universe can have three possible geometries, dictated by the total density of all matter and energy within it. Think of it like the surface of an object. If the density is too high, space curves in on itself like the surface of a sphere. This is a closed universe. In such a cosmos, parallel lines would eventually converge, and a triangle's angles would add up to more than 180 degrees. If you traveled far enough in a straight line, you would eventually return to your starting point. If the density is too low, space curves outward in a saddle shape, an open universe. Here, parallel lines would diverge forever, and a triangle's angles would sum to less than 180 degrees. But if the density is exactly at a critical, razor-thin value, space is flat. This is the unstable knife edge. The problem is that any tiny deviation from perfect flatness in the early universe would have been magnified catastrophically over billions of years of expansion. If the infant cosmos was even slightly curved, that curvature would have grown exponentially. A 1% deviation from flatness a second after the Big Bang would have ballooned into a universe that is either wildly closed or gapingly open by today. For our universe to appear as flat as it does now, after 13.8 billion years, its density in the first moments must have been fine-tuned to an accuracy of 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros, a number so incomprehensibly precise it is like balancing a pencil on its tip for billions of years and finding it still perfectly upright. The odds of this happening by random chance are effectively zero. This is the flatness problem, and it screams that something must have forced the universe into this precise geometric state. Once again, the leading solution is cosmic inflation. That brief, violent period of exponential expansion would have acted like a cosmic iron, stretching any initial curvature in the primordial universe flat. Imagine the surface of a wrinkled balloon. If you inflate that balloon to the size of a planet, any small wrinkle or bulge becomes imperceptible, and the surface appears perfectly smooth and flat from your local perspective. Inflation did exactly this to the fabric of space-time. It took whatever geometry the universe had at birth and stretched it so enormously that any curvature became negligible across our entire observable horizon. The flatness we measure today is not a miraculous coincidence, but a direct prediction and a lasting echo of that inflationary spasm. It is the geometric fingerprint of the universe's most violent growth spurt, a permanent monument written into the angles of distant light telling us that our reality was once smaller than an atom and smoother than anything we can comprehend. That perfect engineered flatness forces us to confront the engine that created it. Cosmic inflation is a breathtaking solution to our deepest cosmic puzzles, but it immediately presents a new and perhaps more profound mystery. What triggered this violent growth spurt in the first place? What was the universe like in that fleeting instant before inflation began? And what strange force could possibly cause space itself to stretch faster than light? The leading theoretical answer lies in a hypothetical energy field that permeated the infant cosmos, known as the inflaton field. Think of it not as a thing you can touch, but as a condition of space, like a uniform tension or pressure filling every point. In its initial state, this field was trapped in what physicists call a false vacuum. A simple analogy is a ball resting on a high plateau. The ball is in a state of high potential energy, but it is stable for the moment. It is not at the lowest possible point. This false vacuum state possessed a bizarre property. Its energy density did not dilute as space expanded. Normally, if you have a box of radiation and you make the box bigger, the energy inside gets spread out and thins. But the false vacuum energy of the inflaton field remained constant even as space stretched. This created a runaway feedback loop. The energy density stayed high, causing more repulsive gravity, which caused more expansion, which kept the energy density high. This is the self-perpetuating engine of exponential inflation, but such a state is inherently unstable. According to quantum theory, the field would eventually tunnel or roll off its high plateau, down into a true vacuum state of lower energy. This transition, the decay of the false vacuum, is where our familiar hot Big Bang begins. As the inflaton field rolled down this energy slope, it began to oscillate rapidly at the bottom. All that colossal potential energy stored in the false vacuum had to go somewhere. It did not vanish, it was transferred, transforming into a seething, ultra-hot soup of fundamental particles and radiation. In that moment, the universe was flooded with heat and matter, igniting the fiery cauldron we recognize as the beginning of the classical Big Bang. The entire observable universe, all its stars and galaxies, may have been forged from the decay energy of a single, microscopic patch of this inflaton field. Yet for all its explanatory power, the inflaton field remains entirely speculative. We do not know what kind of particle it corresponds to, or how it interacts with the forces and matter we know today. Its properties are reverse engineered to produce the universe we see, but we have no direct experimental evidence for its existence. The energy scale of inflation is unimaginably high, far beyond what any particle accelerator on Earth could ever probe. We are left with a cosmic chicken and egg problem. Inflation elegantly explains the flatness, the smoothness, and the structure of our universe, but the origin of inflation itself is shrouded in a deeper unknown. What set up that initial false vacuum condition? Was it a random quantum fluctuation in a pre-existing void, or the final moment of a previous cosmic cycle? The mechanism remains one of the greatest speculative frontiers in cosmology, a moment of creation that solved the universe's deepest riddles by posing one final, magnificent question of its own. If the inflaton field's decay birthed our cosmos, what if that process never truly stopped? The multiverse hypothesis suggests our universe is not the only one, but a single bubble in an infinite, frothing sea of other realities, each with its own unique laws of physics. This is not science fiction, but a serious, though controversial, extension of our best theories about cosmic inflation and string theory. The idea emerges naturally from the mechanism of eternal inflation. Picture that primordial inflaton field, the energy that drove our universe's exponential growth. In the standard story, it decayed everywhere at once, filling our bubble with hot plasma. But quantum physics is inherently random. What if, in some regions, the field did not decay? According to the math, if even a tiny patch of space remained in that high-energy false vacuum state, it would continue inflating exponentially, even as our own bubble stopped. That eternally inflating background becomes a spawning ground. Within it, quantum fluctuations can trigger the decay of the inflaton field in other, isolated patches, each one ballooning into its own separate, self-contained universe, completely disconnected from our own. This process could be endless, creating an infinite multiverse where bubble universes nucleate forever, like bubbles forming in an endlessly boiling pot. String theory, our leading candidate for a theory of everything, adds another staggering layer. It suggests there may be an astronomical number of possible stable configurations for the extra dimensions it requires, perhaps 10 to the power of 500 different solutions. Each solution corresponds to a different vacuum state, a different set of physical constants and laws. In the multiverse framework, each bubble universe could freeze into one of these configurations at random. In this cosmic landscape, the fundamental forces, the masses of particles, even the number of spatial dimensions could be different. In one bubble, gravity might be repulsive, preventing matter from clumping. In another, the strong nuclear force might be too weak to bind protons and neutrons, so no atoms ever form. Our universe, with its seemingly fine-tuned constants that allow for stars, planets, and life, would then be no miracle, just a rare but inevitable outcome in an unimaginably vast ensemble where every possibility is realized somewhere. This idea carries profound philosophical weight. It offers a potential answer to the problem of fine-tuning, why our universe's laws appear so perfectly calibrated for complexity. If there are infinite universes, we naturally find ourselves in one of the rare ones that can support observers like us, a concept known as the anthropic principle. Yet this very strength is also its greatest weakness from a scientific perspective. Can we ever test it? If other bubble universes are causally disconnected from ours, by definition we cannot see them, measure them, or interact with them. Some theorists propose we might find evidence in the scars of ancient collisions. If our bubble universe, early in its expansion, grazed another inflating bubble, the collision could have left an imprint on the cosmic microwave background, a strange, circular pattern of hot or cold spots. Astronomers have searched for such signatures, but so far none have been conclusively found. The multiverse remains, for now, a breathtaking inference from our most ambitious mathematics, a shadow on the cave wall of cosmology. It stretches the definition of science to its breaking point, challenging us to ask what it means for an idea to be true if we can never, even in principle, verify it. Are we glimpsing the true, fractal nature of reality, or have we constructed an untestable metaphor for our own cosmic loneliness? This endless branching of realities, where every possible universe may bloom, brings us to the final and most mind-bending frontier of all. What if the universe we perceive is not a fundamental reality, but a rendering, a cosmic-scale simulation running on a computer of unimaginable power? This is the simulation hypothesis, a provocative idea that reframes every mystery we have explored not as features of nature, but as artifacts of code. The argument begins with a simple, logical projection. If any civilization, perhaps only a few centuries more advanced than our own, could create conscious simulations that are indistinguishable from base reality, and if they had any reason to run such simulations, then the number of simulated minds would quickly dwarf the number of biological original ones. Statistically, any conscious being, including you and I, would be far more likely to be one of the simulated entities than one of the original creators. It is a numbers game played with the fate of reality itself. The hypothesis gains traction when we examine the very fabric of our universe. Our physical laws are not messy or arbitrary, they are elegantly described by mathematics. From the parabolic arc of a thrown ball to the orbit of a planet, nature follows crisp, computable rules. This mathematical underpinning is exactly what you would expect from a well-designed simulation, where the program calculates outcomes based on underlying algorithms. Furthermore, we have discovered fundamental limits in our own physics that resemble the resource constraints of a computer. Quantum mechanics introduces a pixelation of reality, with discrete packets of energy and a smallest possible unit of distance, the Planck length. This could be seen as the resolution limit of the simulation, the point where you can zoom in no further without seeing the pixels of the code. Even the speed of light, the universe's ultimate speed limit, could be interpreted as a processor clock speed, a maximum rate at which information can be updated across the cosmic grid. To visualize this, picture the vast, swirling galaxy from the previous section, but now imagine a faint green digital grid superimposed over it, like the code view in the Matrix, revealing the cosmic vista as a constructed projection. Yet for all its philosophical intrigue, the simulation hypothesis currently resides outside the realm of testable science. How could we possibly detect the programmers? Any glitch or anomaly we might find, like a strange particle behavior or a statistical fluke in the cosmic background radiation, could just as easily be explained by new physics within a base reality. Proving we are in a simulation is as difficult as software proving the existence of the hardware it runs on from inside the program. This transforms the idea into a modern metaphysical mystery, a mirror for our technological age. It asks us what reality truly means if it can be synthesized. It challenges the very premise of our cosmic quest, suggesting that the 24 profound mysteries we have journeyed through might not be secrets of a fundamental universe, but deliberate puzzles, hidden features, or even unresolved bugs in a grand design far beyond our comprehension. The simulation hypothesis does not provide answers. It reframes every question, leaving us to wonder if we are explorers of a genuine cosmos or players in the most immersive game ever conceived. From the possibility that we are living in a simulation to the very real force tearing galaxies apart, this journey has charted the edges of our understanding. We have seen that the universe's expansion is not merely a physical fact, but a metaphor for the ever-widening horizon of our ignorance. Each of these 25 mysteries, from the ghostly pull of the great attractor to the fleeting shout of the wow signal, represents a frontier. They are not failures of science, but its very engine, the unanswered questions that propel us to build better telescopes, dream bolder theories, and look deeper into the dark. We inhabit a cosmos where the dominant ingredients are unknown, where the laws of physics break down at the edge of a black hole, and where the past and future are written in a language we are still learning to read. This is the true wonder, not that we have figured everything out, but that the universe remains so magnificently, humblingly strange. It invites us not to be intimidated by the unknown, but to be inspired by it. So now the question turns to you. Which of these cosmic puzzles keeps you gazing at the night sky? Does the silence of the Fermi Paradox haunt you, or does the phantom tug of dark energy spark your imagination? Share your thoughts in the comments below, and if you want to join us for more journeys to the edge of understanding, be sure to subscribe. Our universe is expanding, and the adventure has only just begun.